So now we're going to go ahead and look at some questions from our textbook out of 1.4. Again, if you want to go back and see some of the worked out homework questions out of 1.3, it's posted in Canvas for you. There's a video link. We'll always post the notes and the video so you can go back and look at things. And I worked out about 10 of them. I didn't work them all out, but I got you to the point where you could look at the equation and solve it. So if you're struggling with 1.3, go back and look at some of those. 1.4 is very similar to 1.3. They're almost identical to each other. It's just that we're going to be looking at distance problems today, and also problems that involve denominations, which is very, very similar to the mixture and the investment problems. So we're going to begin with question number 11, and this is on page 97. And this is very, very similar to the investment and the mixture questions out of 1.3. What we're looking at is two different types of coins, so they're worth different amounts of money. And we're going to have the denomination, the worth of these coins, how much each one is worth. Then we're going to have the number of coins, and then we're going to have the value of the coins put together. So let's go ahead and look at number 11, and this again is on page 97. In Canada, there are $1 coins called loonies, because they have a picture of a loon on the reverse, and $2 coins called toonies. When Marissa returned home to San Francisco from a trip to Vancouver, she found that she had acquired 37 of these coins, with a total value of 51 Canadian dollars. So how many coins of each denomination did she have? Well, what we want to look at first is we want to make our picture, just like we did out of 1.3. It's really no different. And again, this is on page 97, question 11. So I'm going to use dollar signs to represent these coins. And over here, we're going to have our total coins. And we've got two different types of coins. So we're going to have coins. And we're going to look at the denomination. So if we've got two different types of coins, we've got coins that are worth $1 a piece. And we've got coins that are worth $2 a piece. So that's what we have. And do we have a total number of coins? Yeah, if we read the question, what does it tell us about the number of coins? Well, it says these coins totaled together. We're not looking at the value of the coins. We need to know how many total coins we have, and we have a total of 37 coins. Now that value, that's like the pure, or the interest that we did in the investment problem. So that's going to be a different part. That $51 is going to be used in a moment. But right now, we want to know how many coins we have and how much are these coins worth each. So they're worth $1 or $2, and we have a total of 37 of them. Now, do we specifically know how many $1 coins that we have? Does it tell us in this problem at all? It doesn't, does it? It just says we've got some $1 coins and we have some $2 coins. So we don't know how many $1 coins we have. So we're going to use an X there, okay, because that's unknown. Do we know how many of the $2 coins we have? Nope, we don't know either. Now we can't use X again. So what do we have to use? The total number of coins minus X there. And how many total coins do we have? Nope, that's the amount of the coins. That's how much they're worth. We have a total of what? Yep, 37 coins. So that's going to be 37 minus x. So we're not working with the 51 at all yet. Why not? Because the 51 is the cash value of these coins. The 37 is how many physical coins I have if I laid them out on the table. So I have 37 coins on the table. We call the first one x. We call the second one 37, which is our total number of coins, minus x. And those x's now, they do what? Cancel if you add across, because one is positive, one is negative. Now let's look at our value. And the value of these coins is going to be the number of coins that we have times the denomination. So the number of coins times the denomination here. Okay, and it's Madison, isn't it?
Yes.
Yep. So what do we have on our first one? Well, for our first one, we've got an unknown number of coins, x, and those coins are worth $1 a piece. So we have 1 times x, which is just simply going to be x. What about the $2 coins? Well, they're worth $2 a piece, right? And how many of those do we have? Unknown, but that's 37 minus x. And what's our total value of all the coins put together? How much if I went to trade those coins in would I get?
51.
Yep, I would get the 51 here. Where students make a mistake on all these type of problems is they get these two numbers mixed up. Number of coins goes here, value of the coins goes here. Now we should be able to just solve it by simply distributing through, combining like terms, and finishing it. So we'll just quickly solve it here. And we've got now an x, and we've got 37 times 2, that should be 74, minus 2x equals that 51. Combine those together, so minus x plus 74
Can you move the paper?
equals 51. Yep, I will. Sorry about that.
You're okay.
So there's our equation, and we just simply combine like terms there. Now we'll move that 74 over. Now we've got minus x equals a minus 23. We'll divide by a negative 1. And that now leaves us with x equaling what? X equals now 23. Okay. Now a lot of times students get confused and start doubting themselves here.
Yeah.
When they see this minus x, they think, and that minus 23, they think, well, number of coins can't be negative, right? But when you divide by that negative, it becomes positive, so it works. So when you start solving these things, don't worry so much about what it is until the end. At the end, when you solved it, make sure it makes sense. 23 seems legitimate, right? But sometimes students will see that minus 23 over here, and they'll forget about the negative here, because when you divide through, then it becomes positive. But sometimes students will start doubting themselves at this step.
How did we use the negative x?
Okay, how did we get the negative x? Well, we have a positive x and a minus 2.
Oh, okay.
Yep.
That makes sense now.
Yep. Okay, does that make sense for everyone now? Okay, let's go ahead and answer our question. So what do we have? We want to know the number of each type of coin. So we have the 23. Now, what does the 23 go with? The $1 coins. So we have 23 coins that are worth $1 a piece. And we also want to know how many coins that we have that are worth $2 a piece. Well, how do we get that? Okay, if we know one of them, how do we get the other one? Okay, plug it back in, and that's going to be 37 minus 23 And 37 minus that 23 gives you now 14. So now we have 14 coins at $2 each. We can easily check and make sure that our answer seems applicable. Why? Well, how much should these coins be worth total? They should be worth total $51. Now, 23 coins at $1 a piece, those are going to be worth $23. 14 coins at $2 a piece, they should be worth $28. And if I add them together, what do I get? $51, so I know that I did it correctly. You can always check them by just simply finding out the total value, and it should be 51. Also look at the coins. How many total coins do we have? 37. If I add these together, do I get 37? Yes, I do. So you can check it a couple of different ways. Let's try a similar question. And let's look at question 16. And this one's very similar. The only difference is, instead of looking at coins, what are we looking at? We're looking at some tickets and the cost of these tickets. So question 16. For a high school production of Hello Dolly, tickets cost $5 for the non-student, $5 each, and non-student tickets cost $8. If 480 tickets were sold, and the total value was $2,895, how many of each type of ticket were sold? Very similar. Only difference is, instead of coins, we've got tickets. So we're going to set it up in almost exactly the same way. So we've got number of tickets. And you can do denomination, you can do price, whatever you think makes sense for you. So let's just do tickets and the price of each ticket. And on the right-hand side, what do we need? Total tickets. So we've got some tickets that we've sold, and we want to know how many of each type we have. Well, we have two types of tickets. We've got tickets that cost $5, and we've got tickets that cost $8. Is everyone okay with that so far? Right? Two types of tickets, and we need a total number of tickets. So how many total tickets do we have? Do we sell? Not the value of the tickets. Number of tickets is what? Number of tickets is going to be 480. Right? So 480 tickets. Do we know how many $5 tickets we sold?
No.
Nope. So that's going to be an X there. Do we know how many $8 tickets we sold? Nope. So what's it going to be? Total minus X. So that's 480 minus X, right? Is everyone okay with that? So one is X. The other one is the total minus X, which that's, in this case, 480 minus X. Now we can build our equation. And we're going to look at the value of each type of ticket. And the value is going to be the tickets sold times the price. Is everyone kind of okay with the setup? Is everyone all right how I set it up? That's the main part, is where students struggle is the setup. Normally the solving is not as much of a problem. It's the setup. Okay, so we want to get our value, and that's the number of tickets times the price. So let's go up and look. We'll call this one number 1. And what do we have on our first type of ticket? Well, they're worth $5 a piece. Unknown amount, X, so that is 5X. Okay. Second one, what do we have for it? $8 tickets. And how many of those do we have? 480 minus X. And over here, we're looking at the total cost of all the tickets. Now, you can, again, label them however you want. Total value, total cost. How much did all the tickets put together cost? From our question, the total cost of all the tickets put together was $28.95. So that's going to go over here. Okay, is everyone okay with how I set that up? Now again, where do students make the mistake? They get the 480 and the $28.95 mixed up. So make sure you know, total tickets goes down here, total cost is down below. Distribute that 8 through. So that's 5X plus, we've got 8 times that 480. That's 38.40 minus 8X, and that equals our $28.95. All we have to do is combine terms together. So 5X and a minus 8X, that leaves a minus 3X. And I'm going to go ahead and move that 38.40 over. So I think we can do that all in one step here. So I just combine like terms, and I'll move that 38.40 over. 28.95 minus that 38.40 gives you a difference of minus 9.45. Divide by our negative 3, and we now have it. Negative over negative makes it a positive. And that's 3.15. So is everyone okay with what we did? So we got our equation. We distributed that 8 through. We combine like terms. Now you can do it in separate steps, but I think we should be able to see that we can combine those together here and move that 38.40 over here. Now, what's our answer going to be? Okay, we want to know how many of each type of ticket that we have. So we have 315 tickets at $5, right? Those are going to be the $5 tickets, 315 tickets at $5. And we need to also know the $8 tickets. How do we get that? Well, that's going to be 480 minus 315. And 480 minus 315. Make it look clearer here. So 480 minus 315 is a difference of 165. So we've got 165 tickets at $8 a piece. And if we wanted to check, we could easily check it. Because how could we check it? Well, how much are these tickets supposed to be worth total? $28.95. Let's see if it actually does that. So we've got 315 tickets at $5 a piece. That's $15.75. And we're going to add in 165 tickets at $8 a piece. That's $13.20. And what does that give you? $28.95, which it should be. So you can always check them by simply multiplying and make sure the value of the tickets is correct. Also, 315 and 165, what does that add up to give you? 480, which should be the number of tickets, which it is. So we know that we did it correctly. we've got one more type of problems that require a diagram. And then we'll look at some easier ones. So these are the more difficult ones. We are going to now look at distance problems next. And they're very similar to, and they're actually a little bit easier, I think, very similar to the mixture and the investment problems. When we talk about the distance problems, we've got three things that are involved. We've got the rate of speed, and that's going to be your miles per hour. So it's going to be miles or kilometers per hour. So you've got a rate of speed, and that's either going to be in miles or kilometers per hour. You've got a time, which is the number of hours, and you've got a distance. And what's your distance? Distance is either in miles or kilometers, right? And how do you find the distance? Well, the distance is going to equal the rate of speed times the time. And we may just not have thought about these, but every time we drive a car or do anything, whether that's walking, driving a car, what do we have? We have three things that are going to be involved. How fast am I walking, or how fast is the car going? Okay. How long does it take me to get to the destination? Number of hours. And how far am I traveling? And that can be either in miles or kilometers. And remember, your distance is going to be equal to the rate of speed times the time traveled. Now, the main difference between these distance problems and the investment and the mixture problems is the fact that it can either be addition, subtraction, or they can equal each other. And how we determine whether it's addition, subtraction, or if they equal each other is we look at what are called vectors. And these illustrate the direction. If I've got two cars going in the opposite direction, like this, they add together. If they're going north and south, they add together. Okay, so anytime they go in opposite directions, they add together. So when we draw our diagrams, if they're going in opposite directions, they add. When do they subtract? Yep, when they overlap, right? When they overlap, they have to subtract. So these are going to overlap from each other, right? So they subtract. And that's like two people running in a race. We want to know how far apart they are. So we have to subtract their distances. So if they overlap and one is bigger than the other, they subtract. And where can they equal each other? Well, they can equal each other when they're the same size and one's going to work and one's coming back home. So if you're looking at the distance going to work and coming back home, it should be the same, right? If you use the same route, the distances should be the same. So when we look at our applications, it's going to either be addition, subtraction, or they can equal each other. Those are the options that we have. So that's just one added step, but the actual problems are easier. So now let's look at two of these. And let's look at, how about we look at question number 22. Okay, this is a pretty easy one. We're going to look at question 22. Now don't worry about the table. We're not going to make a table like that. The textbook uses tables, but I think the tables are more confusing than just drawing a diagram. So we're going to draw our diagram. It's the same as the table, but I think it's less confusing for students. So question 22. A train leaves Kansas City, Kansas, and it travels north at 85 kilometers per hour. Another train leaves at the same time, and it travels south at 95 kilometers. How long will it take before they are 315 kilometers apart? So when I come to this type of question, this is a distance question, and that means I've got to figure out first if it's addition or if it's subtraction. Okay, so let's draw our diagram so that we can see what we've got. Now, what do we know? We're going to start here in Kansas City. And one train is going north, one train is going south. So what do I know about this now? Just by looking at our picture, I already tell they're going to add, right? Because one's going north, one's going south. Opposite directions, so they add together. Now, each of these is going to have a rate and a time. And then we calculate our distance. Right, so let's go ahead and fill this in for each one. So what do we know first off? Well, we've got a train that's going north. Okay, and this train that's going north is going at 85 kilometers per hour. And do we know the time of the train going north? No, it doesn't tell us at all, does it? It doesn't give us any times at all. So we don't know. You can either use the variable t or you can use the variable x, either way. I generally will use an x because we normally work with x. So we'll call our time x. What about the second train? It's going south. And how fast is the second train going? 95. Now they leave at the same time. Do we know how long the second train is traveling for? Nope. We don't know how long the first train is traveling for, but they leave at the same time. So that means the second train is also has a time of x. Now you can label north-south, however you want to label them. I'm going to use a 1 and a 2. And now let's find our distance. And our distance again is the rate of speed times the time. And I think these are actually a little bit easier to solve. Okay. First train. 85. Unknown amount of time, x. Second train. 95. Unknown amount of time, x. What are they going to equal? Well, they need to equal the total distance. And what's our total distance from the problem? 315. Now we've got something that is going to be very, very easy to solve. So add your 85 and your 95 together. That gives you 180. X equals your 315. Divide by your 180. And now we've got x equaling, when we divide here, 1.75. And you can express this a couple of different ways. You can leave it as a decimal. On applications, you can leave them as a decimal. So you could write it as 1.75 hours, or you could write that as 1 3/4 of an hour, or you could write that as 1 hour and, 45 minutes. I would take either of these three. Doesn't matter which one you choose. They're all the same. So unless it specifically tells you how many minutes, 1.75 is fine with me. If you want to write it as a mixed fraction, that's okay as well. And if you want to break it down into minutes, you can also do that. So either of these three will work. Most of you will probably leave it as the easier one, as 1.75 hours, and that's okay. The main thing is just making sure that we can solve the question. But again, quite a bit easier once you got the equation than the previous ones. 25. $25 is another distance question. And let's look at 25 here. On question 25, Charlemagne took 3.6 hours to drive to her mother's house on Saturday morning for the weekend visit. On her return trip on Sunday night, traffic was heavier, so it took her 4 hours. Her average rate of speed on Sunday was 5 miles per hour slower than on Saturday. What was her average rate on Sunday? So first thing we need to do is we need to figure out if this is addition, if this is subtraction, or if this equals. Well, if we're going to your mom's house and we're coming back, that distance should be the what? The same, right? They should equal each other. And that is question 25. So if you're going there and you're coming back, they're going to equal. Saturday we're going there, and Sunday we're coming back. That means these then should equal each other. And we need a rate, and we need a time for each one. So let's start with Saturday. Okay, so Saturday, she leaves to drive to her mother's house, and that takes 3.6 hours.
Jeez.
So she lives quite a ways away, so that's going to be 3.6 for the time. Do we know how fast she's going? Nope, doesn't tell us at all. So we're going to use an X to represent that rate of speed. So we don't know how many miles an hour she's traveling. We don't know. Now, Sunday, what happens on Sunday? Well, Sunday, she comes back, but there's a lot more traffic, and it takes her 4 hours instead of the 3.6. So that's going here. And she also is not able to go as fast. And it says her average rate on Sunday is 5 miles an hour slower. So a rate on Sunday is going to be X minus 5 because we're traveling at 5 miles an hour slower. Is everyone okay with that so far? Can we see how we got that set up? Now, what do we know here? We're not going to add them together, right? We're going to do what? Set them equal. Because the distance from Saturday to go home should be the same, right? If it's 30 miles to your mother's house, it's 30 miles back home. You can't change that. It's the same. So that means your distance on Saturday and Sunday should be equal to each other. And how do we find our distance? Distance is the rate of speed times the time. And we know they should equal. So the distance to your mom's house going there Saturday morning should be the same as coming back Sunday evening. Okay, so we've got that. Now let's go ahead and build our equation. What do we know about Saturday? That's this one here. Rate times time, so that's 3.6x. So easy enough there. What about coming back on Sunday? That's 4 for the time. And how fast are we going? X minus 5. There's our equation. Okay. And we can now very quickly and very easily finish it. So we've got our equation. Let's go ahead and solve this out. So distribute that 4 through. That's going to be 4x minus 20 here. On the other side is your 3.6x. So that's what we've got there. Again, these are going to be a lot easier to solve than some of the others, because we don't really have to do a lot of algebra here. We are going to move that 4x over. Watch your decimals. Be careful with those. So 3.6 minus 4. It's a minus 0.4x. And that equals your minus 20. We're going to go ahead now and divide. And we'll divide that by a minus 0.4. Yep, sorry about that. And what does that give you? Negative over negative makes it positive. And so x now comes out to be, divide 20 divided by that 0.4. That comes out to be 50. Now let's make sure we answer the question. What is this 50? This 50 is the rate of speed, right? Let's make sure that's what we want. When I read this question, it says specifically, what was her average rate on Sunday? Okay, so this is the rate of speed. And what is this on? Is this on Saturday or Sunday? Saturday.
Should we do minus 5 then?
Right, so we want the other one. So how do we get the other one? This is the average rate of speed on Saturday. We want the speed on Sunday. Well, what would that be? That would be then x minus 5. And so that's going to be 50 minus 5, which is then 45 miles per hour. So on Sunday, she's traveling at 45 miles an hour. Sometimes it may want the distance. Sometimes it might want the rate of speed. In this case, it wanted the rate of speed, but if it would have asked for the distance, you could have gotten that as well. I am going to help you set up one of the questions from your homework here. Okay, let me find one that's going to work for us. Question 10 is one that a lot of times students struggle with about how to set it up. Question 10 and 11 are very, very similar to each other. One's an airplane with wind. The one that we're going to look at is a boat and the stream speed. So the speed of the stream is 6 miles an hour. If a boat travels 80 miles downstream, in the same time that it takes it to travel 40 miles upstream, what is the speed of the boat in still water? Well, we already know that they're going to equal because it says what? Same time. Now, we are going to have to draw a diagram and see how all this goes together. This one is a little bit different. How is it different? Well, we have another factor that's going to make either the boats go faster or slow them down. And what's that going to be? That's going to be that stream. Okay? Now, the stream can either make the boat go faster or slow it down. Just like wind in an airplane. It's either going to speed up the airplane with the wind or slow it down. So I'm going to set up now homework question number 10. So this is, just to make sure everyone knows, this is your homework. 1.4, question number 10. When we read this question, it says the speed of the stream is 6 miles an hour. So I'm going to draw the stream going in this direction. So we've got the stream speed over here, and that's 6. Now it's either going to add to it, or it's going to subtract from it. We don't know the speed of the actual boat, so x is going to represent the speed of the boat. Because that's unknown. We don't know the speed of the boat. Okay, there's a maximum speed that that boat can go, and the current is either going to add to it or subtract from it. So the stream has a speed of 6 miles an hour. And we've got an upstream and we've got a downstream. Now when we talk about upstream, that means we're going up against the stream. When we go downstream, the current's going to push with it. So this is going to be your upstream, and this is going to be the downstream. So what do we know so far? Speed of the stream is 6. That's listed there. Draw a diagram. If a boat travels 80 miles downstream, so 80 miles downstream, it's going to go here. And this is our distance. And that's going to be your 80 there. In the same time, so this one is going to be a little bit different because it's working with the times. Normally we work with the distance, but this one makes us work with the time. In the same time that it takes to travel 40 miles upstream. So the distance upstream is 40. How does that stream affect it? If I'm traveling upstream, what happens to my rate of speed?
Slows down.
Right, it slows down. Now, what's the speed of the boat with no current on that at all? In still water, that boat is going unknown amount of speed, x. So the distance would be x. If I'm going upstream, then that stream is forcing it backwards. So that rate is going to be x, in this case, minus what? Minus 6, because it's forcing it to slow down. Now, when you turn around and you go downstream, what happens with it? Well, this is making it go faster. So that rate of speed would be x what? Plus 6. This one is a little bit different because we're not going to be working with the distance. We know the times are the same. And when we talk about the time, well, how do we find that time? Okay, we know that distance equals the rate times the time. Distance equals rate times time. Let's go ahead and solve that for t. If I solve that for t, divide by our r, right? And so what do we know our t is going to be? Distance over the rate of speed. So now we know time is the distance over the rate of speed. So if it says the times are the same, we have to work with the time. And how do we find the time? Time is a ratio of the distance divided by the rate of speed. That's going to give you the time. Now, how does it work? I'm going to set it up, and you're going to solve it. But we've got the upstream, and we've got the downstream. And it says in the question that these should be what? Equal to each other. So what about the upstream? What do we have for the upstream? Let's go back and look. Okay, 40 on the top. And what's the rate of speed down below? X minus 6. So the 40 is your distance, right? X minus 6 goes below. What about traveling downstream? What's my distance downstream? 80. And what's the speed going downstream? X plus 6. I'm going to do one more step, and then you can finish it. How do we solve this? I know it might have been a bit since we looked at these. Yes, we cross multiply. Okay, that'll clear out your fractions. So we're going to cross multiply. That's going to leave you now with 40 times x plus 6 equals 80 times x minus 6, and you can finish it from here. Right? So that should let you finish it from there. So you'll solve it out. You'll find x, and x is going to be your answer because x is the speed of that boat. You'll set up the problem for question 11 in a very, very similar manner. The only difference is instead of a boat, you've got an airplane, and instead of current, you got wind. That's the only difference. Everything else is exactly the same. Now let's look at a quick angle problem before we take a short break. So just one angle problem. And then we'll take a short break. These are very easy. The next ones, I think you're going to find to be almost a breath of fresh air compared to the applications. Now, when we look at these, we need to know about a triangle. So in a triangle, all the angles sum to 180. Remember that? Okay, so when we look at a triangle, we know that they all add up to give you 180. So these are going to be much simpler than the others. Let's look at question 33. Then I'm just going to draw up our triangle on question 33. This is on page 99. So you can go to your textbook if you want to, or I'm just going to draw up the triangle for us on the screen. Okay, so there's our triangle, right? We're going to solve this, and we know that they all add up to give you what? 180. Now, here's where students don't answer the question correctly. We're going to solve it, and we're going to find x. Now, x is not going to be our finished answer. What we do is we take that value of x and we plug it back into the triangle, and we get all three angles. So when you're finished, you should get 3 answers. Not just x, we have to get 3 answers. So let's go ahead and solve this one out. What do we know? We know they add together to give you 180. So don't make it any more difficult than what it needs to be. You just sum together to give you 180. So 3x minus 36 plus x plus 11. That equals 180. Simple enough. They always equal 180. Combine like terms. So let's see what we've got for x's. We've got 3, 4, and 5 x's total. And then we've got a minus 36 and a positive 11. 36 is the larger number, it's negative, so our answer is going to be negative then 25, and that equals now 180.
Okay, I feel like this is a lot easier.
Yep, and they are. I told you, these are going to be a lot easier. The questions we're going to look at in the last part of 1-4 are almost a breath of fresh air compared to some of the others. So add the 25 over. And now we've got 5x equals, what is that, 205? Plus 25, yep, that's 205. We'll divide by our 5. And that leaves us then with x equaling 41. Now, where students make a mistake is they stop here. This is not going to be our final answer. Everything we've done is correct so far, but we need to get the 3 angles. So we need all 3 angles. So what's our first one? Well, if we go back up and look, you can look at it in any order that you want. Okay, one of the angles is 3x minus 36. So that's 3 times 41 minus your 36. Okay, so we'll work that one out, and that's going to be one of them. 3 times 41 is 123. Subtract off your 36, and one angle is 87 degrees. Another one is x plus 11. So that's 41 plus 11. That should give you then 52, I believe. And that's going to be 52 degrees. And then what's our last one?
41.
Yep, our last one is simply x. Right? And so it's just going to be then 41. And how do we check? Well, they should add up to give you what? 180. Do they add up to give you 180? They do. Let's go ahead now and take a short break. We're going to come back, and then we'll look at more angles. We'll look at vertical angles, and we'll look at complementary and supplementary. So let's meet back here at about 9:40. So meet back here in about 15 minutes at 9:40.